Good morning.
Good morning.
Good morning. Good morning. Okay, so any questions? Okay, so we will continue on the chapter 20. We are at one example. We finished part of that example. So this example has part A and part B. So in part A, we want to calculate few things. Want to calculate the E cell and then calculate delta G 0, then the equilibrium constant K. For this equation as written, 4 Ag solid plus O2 gas plus 4 plus aqueous. So this first equation. Then in the second part of the question is calculate, again do the similar calculation for E delta G and K, but for a different way of writing the reaction for this reaction. So this is for part B, and this is for part A. So we did the first part Tuesday, and let's just quickly review what we did. So if you are given a chemical reaction, you want to calculate the E cell, you just identify in this equation what is on the cathode, what on the anode. And we can see in this reaction as written, the Ag solid has been oxidized, and oxygen gas has been reduced. So Ag will be on the anode. So oxidation for the Ag, reduction for the oxygen. So we have this two reaction, and so we have those E reduction at a standard condition, and then we'll use the cathode, which will be this reaction O2. So 1.23 minus 0.80 get 0.43 volts. 1 point we noticed Tuesday. So even though in this equation we have 4, 4, and 4, but this number you get actually is from this equation. So you get Ag plus aqueous plus 1 electron produce Ag solid. So this is this number. Okay? So this number. And then, so just a couple of points we want to notice. Even though in this equation we have 4 and 4 and 4, in this equation we only have 1, 1, and 1. We still use the same number. So for this equation, we write E0 reduction equals positive 0.80 volts. So this is 1 point we want to notice. Another is this reaction right is for the oxidation, but this reaction right is from the table. So in the table, every equation is written as reduction. So therefore, even though this is written as oxidation, but we're still using this reduction number in the calculation. So these are 2 points. We can use that because we have this formula to take care of that. So we use this negative sign to make sure we subtracting the number from the anode, and so therefore here we don't have to inverse the sign. Okay, so once we get the E, we use one equation. We know there's a relationship or the connection between E and delta G. So we plug into the number for E, then we identify what is F. So F is the Faraday constant, and N is the number of electrons transferred in the overall equation. So in the overall equation, we say we have 4 electron transferred. So that's how we calculate delta G from E. So those numbers become very, very large numbers. So when the number become very large, you probably, when you're running early or later, you probably will get the same magnitude, like 10 to the 29, 10 to the positive 29. But how much 10 to the positive 29? Here the 10 to the positive 5, because this is delta G. So this delta G is very, very negative. So then next, you want to calculate K. So using the equation for K, like one equation you can use for K is this equation. So if you know delta G, you can calculate the K. But because K becomes so big, it's become very sensitive to the roundings. That I said you still get a positive 29, but this number might vary, might change. So some people, if running early, might get like a 2 or 3. So when you have those questions on the multiple choice exams, just pay attention to this exponent. Okay, so now we are going to start on the second part of this question. So the second part of the question is we think about this equation from part A. So then we are going to do something about this equation in part B. So this is from A. So what you do in part B is multiply the equation from part A by 1/2. So you know how to multiply equation by 1/2 or by 2 by some numbers. You just multiply every coefficient by 1/2. So 4 multiplied by 1/2 become 2. 1 multiplied by 1/2 become 1/2, and so on. So get this equation, this new equation. This will be the new equation we are going to do the calculation for in part B. So same idea. You want to calculate the 3 things. You want to calculate what is the E cell, what is delta G, what is K. Once you know that, you want to starting with calculate E. So therefore you identify what is the reduction, what is the oxidation. So you will take the number for the reduction minus number for the oxidation. So you still get the same number as we noticed in part A. So no matter you use 2 or 4 in part A, you will use the same number because this guy E reduction is a so-called intensive property. So it does not depend on how much we use. So as a result, we still have the same number. You can call this E cell in part A. So the E is still the same, is positive 0.43 volts. But the delta G and K will change because the equation to calculate delta G is this. This is not right. So let me write the equation. So delta G equals N, negative N F E cell. So even though E cell is still the same, F is still the same because F is constant, but N changed. So therefore, the E cell does not depend on how we write the equation because that's X intensive. So this delta G depends on the way we write the equation because this depends on N or X intensive. So therefore in part A, this number here is 4, but now we have 2. So therefore, we will have a different number for the delta G. All right. So therefore, once we get delta G, we will do the same calculation for the K. So this equation comes from this equation. Remember, we have delta G equals negative R T L N K. So what we did using this equation substitute. So we have this number for delta G. So this is delta G. Then this is R. Then this is T. So we want to find out the K. So therefore, you do the similar calculation, multiply, divide, take the exponential, you get K equals 4 times 10 to the 14. Okay, so the comment about this question is E0, or sometimes we don't have to say the E cell. The E cell is an intensive property. To multiply chemical equation by some numbers will not affecting the value of E0 cell. But delta G is extensive, so therefore multiply equation will change the value of n. However, so therefore the value of delta G, because delta G is extensive. So does the K. So K is also extensive. So therefore, when you multiply equation by some numbers, you will change the value for the K. All right. Any questions? Okay. So now we know most of the time the chemical reaction happens at non-standard. So this notation here is standard. But a lot of time your chemical reaction is not standard. So then how do we calculate those quantity like delta G and E cell at non-standard condition? So we have this equation for delta G. So in this equation, delta G is at any condition, standard or non-standard. So delta G0 is a standard condition. So then R is constant, T is temperature in Kelvin, Q is the reaction quotient. Which have a similar expression as K. So therefore, if we know the concentration, partial pressure for all those reactant products, we can calculate what is the Q. So therefore, we can calculate the delta G, because we know we can calculate the delta G0. Okay, now in this chapter, so this is in chapter last chapter. So now in this chapter, we learn the relation or the connection between delta G and E is this, non-standard. So this equation is true for any condition. So non-standard, we have delta G equals negative NFE. Then you can imagine what is the equation for standard. So standard, we will have a delta G naught, and E naught. You still have the same number of electrons, same Faraday constant. Okay, so once we have these two equations, we plug into here, and we get this new equation. So delta G, so this was delta G, so this was delta G0. We replace them by this and by this. So we get this equation, and just do like a little bit of manipulation of this equation. So what we do is divide both sides by this. I think yes, last night I just find out if you have the notes ready, I missed this negative sign, so therefore you want to make a note. So once we divide by negative NF, we get this people's name equation, Nernst equation. So this equation you are going to use quite a few problems. So you can just memorize this equation. The next few different version of this equation is like this. So you can change. So this Ln is E equals 2.7 something based logarithm function. So this is the time based. So everything is the same, just change the base to get this number. So in the old days, people don't have calculators, so they using the slide rule to do the calculations or the tables. So therefore, they use that. And even more like convenient in the old days. So they plug all those numbers in. So they know R. So they know R equals 8.314. F is Faraday 96485. And then temperature is usually that. So therefore, you get a very simple version of the equation. Very convenient if you don't have a calculator. All right. But what I want to say is, you can just remember this equation. But you will see in the next one problem, I will use this equation because those people who write the book still kind of from the early days, so they memorize those equations, so they start using this for convenience. So this practice is, let's say, is you have this equation, and then you can see those concentration for the reactants, concentration for the product, not 1.0. So if 1.0, that's standard. 1.0 is standard. 1.0 standard. So clearly, this equation is happening at a non-standard. So then, what will be the potential? What will be the cell potential? So what is cell potential? You pretty much want to calculate this E cell. Okay. So just using that Nernst equation, so we write E cell equals E zero cell minus RT and F Ln Q. I will use the initial equation. All right. So just a few things before we get the result. You first want to calculate what is the E cell standard. So E cell standard equals E standard reduction potential of the cathode, which means the reduction reaction, minus standard reduction potential. So this guy I write is standard reduction potential for all those known reactions. So then that means anode has oxidation happens. Okay, so just be careful if I give you those numbers. So you can see here both equation is given as reduction. So both of these equations given as a reduction. You have to identify in this overall equation what is the reduction, what is the oxidation. Okay, let's take a look. So we have Pb2 plus in the reactant and become Pb solid. So that means Pb gain electrons, so therefore Pb has been reduced. So therefore you can use this number as cathode. Okay, so therefore we know we have negative 0.13 volts. Then minus the other one will be on the anode, minus 0.76 volts. If you want to check, you see that it's true because for zinc, you start with zinc solid and produce zinc 2 plus ion, so zinc lost electron means zinc oxidized. So therefore you do the calculation, you get 0.63 watts. So this is our E cell at a standard condition. So once you know that, we'll go to the next slide, calculate what is our Q. And then we plug back into this equation to get our E cell. All right. So now let's see what is the Q. Okay. So Q will equals the reactant concentrations at the bottom, so the product so the equation for the Q is similar as, so we'll have Q equals the product concentrations and then the reactant concentration. Okay, if you look back into the equation and you know the product is zinc 2+, and then the reactant is Pb 2+. So then the number given to you is zinc concentration 0.55 molar. You want to use molarities. Then Pb is 1.5 10 to the -3. So we get 366.67 going into that. Okay. So now we know we are going to use this equation. So we know the equation we want to use is E cell equals E standard cell minus RT divided by NF LNQ. So we know R equals 8.314 joule per mole per Kelvin. So T equals, in this example, 298 Kelvin, and N is 2 mole of electron. F equals 96485. What is that? That's the Coulomb per mole. All right. So therefore, let's substitute those numbers. We find out the E cell standard is 0.63 watts. So now let's see minus 8.314 joule over moles. It's interesting to see the unit cancellation. So now we will have this T 298 kelvins. Then we will have this N is 2 mole of electrons. Then Faraday 96485 C over Coulomb over moles. And then we will have this LNQ. Okay. So now let me erase something so that I can write this Q. Okay, any questions so far? You can just raise your hand or just unmute yourself and ask the question. All right. So Q, we know we get. So let's see. Let me write initially what do we mean. So the Q will equals 0.55 to the first power, then 1.5 and to the -3. So both of them to the first power because the coefficient is 1. So now what is 1? So 1 means 1 mole. So 1 mole. Okay. So by the mass rule, when you have the exponent on the logarithm function, so this mole will flip over to the front. So therefore, you get another unit which is mole from that. You see, that does not cancel out because this logarithm is divided, that means it's subtracting, so therefore you actually have two terms, so each term will have the more from those exponents. So once you get that more, then everything will make sense. You can see this more cancel out. So therefore, sometimes the textbook sometimes write the per mole, sometimes don't write the per mole, so kind of confusing. So this more here, this more cancel out, this more cancel out. So this key cancel out. So that what's left over is J over C. So what we know J over C means watts. So therefore we have watts plus minus watts. Right. So you see you still have this 0.63 watts. Then those numbers here multiply and divide. So let's see, we get 0.012839 from multiply those numbers, and then this from this L and Q, 5.904. So this is from L and Q. So altogether we get 0.554 watts, and then we run into 0.55 watts. So that means our answer is B. Okay, so this is how you do those calculations for those problems that is not the standard conditions. So another interesting question is we can see as we do some of the labs, we use the pH meters. So how the pH meter function? So as we said, we know from the lab, the pH meter pretty much electrode. So that's how you use electrode information to calculate the pH. Right. So for this problem, so we know the cell is between zinc and H2. So H2 is the standard, and so we pair these two up. So this will be our anode, and this will be our cathode. Anode, cathode, and we have this reaction. So if a standard, so this means standard. So this is standard. So everything like 1 molar, 1 atm. Okay? So here you have something standard. So your zinc ion concentration is 1.0 molar. Your partial pressure of H2 gas is 1.0 atm. But you don't know what is the concentration of H+. So therefore, we can calculate the H+, and then we can calculate the pH. So to do that, obviously, we need to know the cell reaction equation. So the cell reaction equation is given as this, and you can see here we have the numbers. If standard, we know this will be 1.0 molar, so this 1.0 molar, this is 1 atm. Then your cell potential will be positive 0.76 volts. But this question is, this is okay, this is standard, but we don't know this. So therefore, this is not that. I think that is 0.46 volts. So with this information, we can calculate what is this question mark, which is the concentration of H+. Right. So what we do is first calculating this E cell, so positive 0.7, this E cell is a standard condition. And then we notice in this equation, or equation, there are 2 electron transfers, therefore H2. And then we can set up the equation, the Nernst equation. So you can either use the initial Nernst equation, or can use this simple version to calculate what is your Q. And so everything know. So this is the E cell. So at this condition, And then this is E cell at a standard condition. And those just come from, so from R, T, and F. So we substitute R, temperature, F, we get that number. We still keep this 2 here. So 2 is N. So N is 2. So then we just calculate the Q. So because in this equation, everything you know, you can set the Q. So just some simple algebra, you get Q equals to this number. So 3 times 10 to the positive 10. And next, you review this equation. So what will be the equation for Q? Or the expression for Q? So we know Q have the similar expression as K, so product over the bracket. So product of these two brackets this one. So therefore, we have this equation for Q. It's kind of a mixture. So we have a molarity, partial pressure. So that's okay. So you can, if you have a mixture, just make sure your concentration use molarity, your pressure use ATM. All right. So then next, just substitute. So you know, you just get a Q. You are given this number, you are given this number, you don't know this number, so therefore you have this new equation. So 1.0 times 1.0, so this is for zinc 2 plus concentration for this number. This number is for the partial pressure of H2 gas. So this we don't know. And this is Q from that. So this is a simple algebra. So you multiply, divide, and you get H squared equals 3 times 10 to the negative 11. So obviously this is H squared. You have to take the square root, get the H, or H plus molarity. So once you get H plus molarity, you review what we learned in those acid-base chapters. pH equals negative log H plus, get the pH. So therefore, we have 5.3. So that's how we calculate the pH if we know the cell information. And in the pH meters, so all those calculations done for you by the programs in the electrode. All right. So from this Nernst equation, and we can say we can produce the so-called concentration cells. What that means is from this picture. So the picture at the bottom, you can see you have two compartments or two half reactions, and both of them use nickel and nickel. Okay. So therefore, when you calculate this E cell at a standard condition, so that becomes 0. Okay, because you have on the anode, you have the nickel so oxidized. On the cathode, you have nickel 2 plus ion reduced. So therefore, same reduction potential also becomes 0, but the difference is you're setting up them with different concentration. You can see the concentration for the cathode is much higher, for the anode much smaller, much lower. So this is the nature's tendency, nature's driving force. You know, if you have two concentrations, two solutions with different concentrations, if you just literally mix them together, you know, they will mix and become a uniform concentration. So then this is the driving force to make those cell potentials. So even though we don't mix them together, just simply put this solution over here, but you still have the natural tendency. So this concentration, the high concentration is going to be diluted. So then you can see the final result, both of them have the same concentration. Then you don't have the cell potential anymore. So then how do you get this number? Even though here is 0, so you're just using this equation, okay? And so in this equation, obviously you know that R is 8.314 T, typical temperature 298 Kelvin, and for this question, 2 Faraday numbers, and then you can use this number for the So that will be number for the reactant, and then this number for the products. You get a Q, then you get this number. So that's cell potential. I mean, this is the concentration cells. So what this guy do here? So this from the textbook. So this kind of fish from some oceans. So this guy use some of those concentration cells. So use a lot of concentration cells. So he has like some of those cell, the cell, not our cell, the cell, those biological cells. So in the cell, you have a cell membrane, and then inside the cell, outside the cell, you have different concentration of, let's say, potassium ion or sodium ion. So therefore, produce those kind of batteries. So you said this has a lot of batteries. So altogether, it can produce 500 watts of short pulse. Right. So some application of those cells, so we studied those voltaic cells, electrical cells, is we use them in the batteries, and then old times we have those batteries. So battery you can use in the flashlight. So there are quite a few different types. So first of all, some of those battery can charge. Some of those battery cannot charge. So therefore, primary battery just you cannot charge. That is that. The secondary battery can charge. And then the second usage of those cells is the prevention of corrosion, rusting proof. And then you have those electrolysis, like what you are doing this week's lab. Let's look at a few examples of batteries. So we have one typical battery used a lot, like in your automobile, is so-called the lead acid battery. So that is made with lead and sulfuric acid. And then you have the alkali batteries, most common primary batteries. So later on, people developed those secondary battery can charge, like nickel cadmium, nickel metal hydride batteries. So now modern days, we use a lot the lithium ion batteries. You can recharge it. It's very light, produces more voltage. So what the lead acid battery looks like? It looks like those typically. So you have this anode, then you have those cathode. Or this one is the same. So you have few pairs usually in the battery. So this looks like the battery from your automobile. So in this example, you have like one pair, two pair, three pair, and then more. So you have 6. So in this battery, we have 6 cells. So one battery, one car battery have 6 cells. So each one cell equals 2 point some watts. So obviously altogether get about 12 watts. So another type is the alkaline batteries. So there you use zinc metal. So zinc is a very active metal, easily be oxidized. So use on the anodes, on the cathode, you use this. The kind of the manganese has +4 oxidation number, so want to be reduced. Lithium ion battery, the diagram looks like that. So so that's another type. And then fuel cells. So fuel cells, let's see, what is the fuel? Like the fossil fuels, so in some people's kitchen, they use the cooking gas or methane. So obviously you can also like use that directly without burning it. So another fuel for the fuel cell is hydrogen gas, and so much efficient. Because usually the efficiency by burning the fuels produce heat and then produce electricity is kind of low. But if we can use those chemical reactions of H2 and CH4, so usually they will have those oxidation reduction reactions, then we can make the fuel cells. This diagram shows how the fuel cells work. So in this example, you have this H2 will be oxidized into the H plus, then O2 being reduced into hydroxide, and so that's therefore you can use that potentials. What is the problem with in our daily life? So sometimes you buy a new car, your car gets rusted. I get some of those chemical reactions. So corrosion is oxidation of metals. So what happens, like let's say a common metal we use in human being history. So we know that's iron. So iron is a kind of active metal. Will be oxidized, lost 2 electrons, become F2 plus ion. Then you have water, so therefore this F2 plus ion migrate. So this is kind of your anode, and then this will be your cathode. So so O2 being reduced on the cathode, so overall reaction like that. So then how we preventing that? We use a so-called this terminology called the cathodic protection, which means we'll use a more active metal to pair or coating on the metal we want to protecting. So make the metal you want to protecting, for example, Fe become cathode. So therefore, this name comes from you force the metal you want to protecting become cathode. Then you know cathode probably have the reduction reaction, so therefore your metal will be not oxidized. And so another example of using is the underground like an iron pipe. So how you protecting that from rusting? You can paint, or you can just use some of the wires and connecting to a sacrificial metal, for example, magnesium. So therefore, the magnesium will become the anode, so then this becomes the cathode, so therefore your metal will be not oxidized. And that's also happened in your home when your water heater. In your water heater, they usually they implanting one rod of those magnesium metals, so therefore keep your water heater from rusting and get a longer life of your water heater. So another use of electrolysis. Electrolysis in these two pictures at the bottom, you can see. So you have 2 examples. So one example on the left is molten NaCl. So you don't have NaCl, just table salt. So you heat up the table salt above like 800 degrees Celsius, so it melts. Then you use electricity, use battery. So you force this chloride ion being oxidized, and then you force the Na plus ion being reduced. So we know this not easy to happen because the chlorine gas is a very strong oxidizing agent. That means it wants to gain electrons. So you want to take the electron away from the chloride ion. It's not that easy. So therefore you have to use voltage. Or another way to say that, so that this reaction will not happen spontaneously. Therefore, we have to use electricity to driving these 2 reactions happen like here. So another way to using the electrical cells is to the electroplating. So that's this week's lab. So for example, you want to coating some of those metal looks make those metal looks like shining like a nickel or silver or gold. You just do them in this setting. So you take the metal you want to coating on, like a nickel, then this object, maybe a stainless steel, maybe some plastic, so you want to coating that. So therefore, you want to use nickel metal on the anode oxidize nickel, so nickel ion migrates, and then here use a battery to give some electron on this object, so the nickel plus ion gain electron reduce and coating on that object. Right. So those electrolyses usually are non-spontaneous reactions, and they can occur if you use electricity to drive them. So then the last few questions is about how do we do the calculations for the electrolysis. So we know this terminology is stoichiometry. It's about how much electricity we use, how much those metal we can coating on something, or vice versa. So we have to know some of those, review some of those common units. So we know we can have the current. So this is the current, electrical current, and this is time. So usually you use I for the current. So this is I, and this is T. Therefore, so this is Q. So we have this equation, Q equals I times T. Then we also know what is the Q. Q actually the most electron times the gravity. Okay, so all right. So just last note is n is different than that for the Nernst equation, but Nernst equation is n for the overall equation, and here n in these calculations is for the half reaction. Right. So this diagram shows you the map or the strategy to how to solve those problems. You can go either way. You can go from top to bottom or from bottom to top. Okay. So this question is how much time is needed to deposit 1.0 gram of chromium metal from aqueous solution of chromium 3 chloride. Okay, so what you do is identify if you have this aqueous solution, so you have a chromium 3 plus and a chloride ion. So you want to deposit 1.0 gram of chromium metal, which means Cr solid. So the equation, so this the reduction reaction is this. So that means Cr3 plus aqueous plus 3 electron produce Cr solid. Okay, so what you do, you can first calculate how much moles of this ion. So you can start with 1.0 gram of Cr. So the mole of ion equals mole of solid. So mole of let's see this solid. So probably use our usual way. So we see this that. And then you converting from gram to moles with molar mass. So molar mass of Cr equals 52.0 gram per mole. Therefore, we will use 52.0 gram here and 1 mole of Cr here. Okay, and then you can just use ratios. So we have 3 here and 1 here. Okay, so therefore you can use 1 more Cr and 3 more of electron. Okay, so just a quick review. So where you get those 3, where you get this, where you get this 1. So 3 come from this. So this is 3 here, the coefficient, and that's for electrons, so therefore here. And the other one, so this one here is this one. All right. So once we get that, we can do another conversion to find out what is the coulombs, right? So to do that, we use the Faraday number. So Faraday number tells us for 1 mole of electron, so we have a 98 or 96, 485 coulombs. All right, you can keep going. So next is using the current. Okay? So we were given this current. So when you see 1.5A, so that means 1.5 C over a second, over 1 second. So therefore, we can use that to for the next fraction. So we use 1.5 C and 1 second. So finally, all those multiple choice in the minutes. So then what you do, just use 60 seconds and 1 minute. All right. So therefore, you can use this 1, 2, 3, 4, 5 fractions to solve the problem. So finally, you get 61.8 minutes. You can run into 2 sig figs. So just review what we learned in 10.1.13. You want to keep this right number of sig figs because this current has 2 sig figs. So that's for this problem. All right. So I have a proof question. We know how to work with the Zoom, but last time I get your answer in the proof question. But that means you have to log in. You have to change your Zoom account to when you log into Zoom, you have to use your name. So what I get last time is I have the response, but I don't know your name. So this semester almost over. So instead of like let everyone know how to change your name on the Zoom account, so just let's go use our old way. Let's use our pool everywhere. Just use your cell phone. Try to answer this question. Okay, so I give you 2 reactions. You identify which one is the oxidation, which one is the reduction. Then you go by the definition. What reaction should happen on the cathode? What reaction should happen on the anode? So in the first equation, you have a zinc metal become zinc 2+ ion, then give out 2 electrons. What do you think of the first reaction? Is that oxidation? Probably yes, right? So the second reaction, you have a tin 4+ ion gain electron. The gain electron means what? Reduction. Okay. So then what happened on the cathode? Reduction. Okay. So what happened on anode? Oxidation. Yeah. So you first identify, if I give you 2 equations, so which equation is oxidation? So one way to see oxidation means loss electron. Reduction, gain electron. So then, so oxidation on the anode, reduction on the cathode. All right, did we finish the question? Okay, give you a few seconds, few more seconds. Then we will go on chapter 21. Any questions?
So what was the answer to this problem?
The answer is B. You get it right? No.
Yes.
Okay, good. Okay, awesome. So yeah, the answer is B. Okay, so keep doing that. So probably I will try to have one full question for every lecture. Might give you 1 point. Maybe 2 points, or just all right. Any questions? Any other questions? Okay, so we will move on to the next chapter, chapter 21, nuclear chemistry. Okay, so in this chapter, we are going to study some of those reactions happened from the nuclei. So you have to review some of those common concepts. So the way we write the sample for the isotopes. Okay, you can see for most of the elements, there are different isotopes. So isotopes have the same chemical symbol, same atomic number, but different this number. So this number is the mass number. What is the mass number? Mass number is the number of proton plus neutron. Okay. So those proton, neutron, both of them in the nucleus. So therefore, we call them nucleons. So the number of proton is the atomic number. Atomic number you can find out from the periodic table. The number of proton and neutron together is the mass number. So isotope, we learned that concept in Chem 113. Not all atoms of the same element have the same mass due to different numbers of neutrons in those atoms. There are, for example, 3 naturally occurring isotopes of uranium, uranium-234. The one way to write isotope is using this format, or simply use the commonly 3 way. So spell out the element name followed by this mass number, or using this notation. So this notation, obviously, we miss a number here, but that number can get from the table. So usually you can omit this atomic number. Or you can simply write U234. So 234 is a mass number. Mass number equals proton number plus neutron number. Okay. So what are the difference between these 3 isotopes is the number of neutrons in their nucleus. So some of those nuclei change spontaneously, emitting radiation. They are said to be radioactive. We refer to those as radionuclides. There are several ways radionuclides can decay or radiate, become a different nuclide. We use nuclear equation to show how this nuclear reaction occurs. So the nuclear equation little different than the chemical equations. In a chemical equation, atoms and charges need to be balanced, and this still happens in the nuclear equation, but we will use a little different way to balance their charge and balance their mass. In nuclear equations, atomic number and mass number need to be balanced. So this is a way of balancing charge, atomic number. So atomic number sometimes you put in the quotation mark, not really always atomic number. Because we'll see one particle is the electron. So we'll see, we write electron as this notation, which means 0 makes sense because 0 is the mass number. So in an electron, we don't have proton, we don't have a neutron. So this 0 equals mass number, so that makes sense. And then this -1 here, obviously we don't have a -1 atomic number. So that just gives us the charge for the electron. All right. Mass number usually just number of proton plus number of neutron. Don't confuse with the real mass. So electron obviously has mass, but don't have a mass number. So just review some of those. This table summarize some of those common radiations. Later on we'll have more radiation. So in this table we see alpha radiation. What I mean by alpha radiation? Alpha radiation means some of those radioactive nuclei, so they emit alpha particle. So sometimes they emitting the beta particle or the gamma ray. So now what are they? So what is the alpha particle? What is the beta particle? What is this gamma ray? Alpha particle actually a helium nucleus. So we'll say what are the charge. So that's the this charge is 2 plus. And what is the mass? So this is mass. Then here are some more properties. So the penetrating power is 1, which means what is the power of penetrating something or goes through some of those barriers. So this relatively speaking, so just 1 low. So what is really the nature? So what is that particle? So the helium nuclei. So beta particle, we can see the charge 1 negative, mass this one, penetration power becomes stronger. So what are that? That actually just electron. The electron usually write 0, -1. So this not only an electron, this should be like a high speed electron. All right, so the last one is the gamma ray. So this is not really a physical particle. It doesn't have mass. Not a physical particle. Like an atom or electron or molecule, we can call them particles. So this gamma ray is actually a photon, so high energy photon. Just a packet of energy. So the penetration, so charge 0, mass 0, the penetration power is much, much higher, 10,000 times higher than this larger guy. All right, so this give us a few more type of radioactive radiation or decay. So we saw this one on the last slide, this one on the last slide, this one there. But then we have the positron emission. Positron, which means the opposite of electron. So sometimes you write E, so then you write the positive one. So this is the symbol for the positron. Electron capture, so electron is still electron. So sometimes the electron nearby the nucleus can be captured by the nucleus. All right, so this table summarize those equations and then what happens to those atomic number, mass number during those different type of radiations or radioactivities. So the first radioactivity is alpha emission. So in alpha emission, hypothetical way of writing the nuclear equation is here. So X and Y are different names for the elements or the nucleus. What is common in this product? So this product is our alpha particle. So when the alpha particle have this notation. So when that happens, when you have alpha emission happens, and you can see this atomic number decrease by 2, or the atomic number will happen -2. So therefore you can see, if you start with atomic number Z, then your product atomic number becomes Z -2. Okay? Then what happened to the mass number? So mass number is number A here. So if the mass number for the reactant is A, then the mass number for the product becomes A -4, because you have to balance the mass number before the reaction and after the reaction. So that's how you write those equations. Beta emission similarly, so beta emission produces this high speed electron. So therefore we have the charge or the so-called atomic number -1. We don't have really a -1 atomic number, but we know electron has -1 charge. Okay, so this is notation for the electron. So what happened for this reaction, or for this reactant goes through this radiation and produce this product. So to balance the atomic number, if you start with Z, then you produce a -1 atomic number. So therefore this product will be Z plus 1. So Z plus 1, then -1 becomes Z. So that's how you balance the atomic number. Then you can see the balance the mass number. So A equals A. Positron emission, so this is positron. So positron has no mass number, 0 mass number, but the charge is positive. So therefore, if we emit one of this positron, then your atomic number starting from Z, it must go to Z -1. So you take Z -1 plus 1, you get Z. So therefore, Z equals Z, you balance the atomic number. So then the mass number also balance because positron has no mass number, so therefore A equals A. Electron capture, so therefore we have this electron here. Electron is used, captured, is used. So therefore, if you starting with Z and then you adding a -1, so your product atomic number becomes Z -1. Okay, so this just you can see what happened in the different type of nuclear radiations and how you write the equations. So again, we see in details, alpha decay is the loss of alpha particle. Alpha particle is helium-4 nucleus, which has 2 proton, 2 neutron, or this is the same sample for the alpha particle. So if you are given a problem, you see alpha decay, so one product you know for sure is this alpha particle. So then this one, if I give you this, you can find out what is this by take 92 minus 2, get 90. Then you go to the periodic table, see what is 90, 90 is thorium. And then you check the balance equation. You check balance atomic number. So atomic number for the reactant is 92. For the product is 90 plus 2, so therefore also 92. For the mass number, you start in the reactant 238. Then one product has a mass number 234. The other product has a mass number 4, so 234 plus 4 is also 238. So the beta decay, which means we produce a beta particle, so sometimes use beta, Greek letter beta, or just simply use electron. And you can see this example, we start with iodine, then produce xenon. So you see the check the balance. Atomic number start with 53. If this is 91, so this must be 54. So similarly happen for the mass number. So if we have this mass number 0, and you start with 131, so your product mass number also 131. So gamma emission, you probably not write this in your equation for the nuclear reaction because this has no atomic number, no mass number. It always accompanies to other decays. Positron emission, you just remember positron is an opposite electron. So no mass number has mass, but no mass number, the charge is +1. So if I tell you we have positron emission, so that means the positron is a product. And then tell you who is the reactant, then you can find out who is the product, or vice versa. So you check the balance, atomic number 6, starting with 6, produce +1, so the other one must be +5. Mass number is started with 11, and the positron has 0 mass number, so the other product mass number is also 11. Electron curvature, so electron notation is E -1, 0, so this tells us the charge. You use electron as reactant. For example, if you start with 37, and you will see what will be the number, atomic number for the product. We assume there's only one product. So therefore, that will be 36. Similar for the mass number. So 81 plus 0, 81. All right, I think this is for today, and we will continue here next week. And we'll finish this chapter 21, and then we'll get ready for our exam 3. All right, any questions? Okay, so if you have no question, or later on you have a question, you can come back to my office hour, start at 10:30. Okay, so I'm going to ending the meeting now.